country, Nottingham.
And greetings from a small corner of Derbyshire Dales country. Right, we are zooming into YouTube with Zoom.
We've had about 5 or 6 of these live sessions, and not one person has asked me about the flag in the background.
No, they haven't, have they?
Well, for those that don't know, that's called a red ensign. Okay, it's used by civilian ships or vessels of British registration. It came off my boat when I lived down south. A lot of you recognise what a white ensign is, and that's used mainly by the Royal Navy. That's the St George's ensign, and a blue ensign is used by Admiralty clubs and certain officers. So there you go.
Okay.
Nothing to do with TQ whatsoever.
Right. So how's your afternoon been?
Hectic. I mean, just this afternoon I picked some lemons off my tree in Nottinghamshire and made some fresh lemon juice.
Wow, you are industrious.
Yeah.
You must have a very warm garden.
Yes.
Right. Bear with me a second.
I got them from the fruit bowl, actually.
Just going to switch accounts so that I can see what's going on YouTube with comments. Who's with us? Well, I think we might be a bit early. Oh, here we go. We are early. Well, we're going to have to remind everybody. I'm going to remind everybody who's watching this on demand. This is a fantastic opportunity. Listen to this video, watch this video to hear top tips from Digital Dave, where he explains about how to decommission pieces of apparatus if you might be shutting the lab down for a few months. We'll be looking at some questions that have come in from the audience. They might be about structures, they might be about engines, they might be about control engineering. Do stay on the line, do stay on and watch this video to see what we have there. You can put your comments in the comment box below, and if you're liking this, please do like, share, and maybe subscribe to the Tech Equipment YouTube channel if you're not already doing that. Dave, on your travels with Tech Equipment, how many countries do you think you've been to?
70 or so.
Wow.
Yeah.
Wow.
Yeah.
And typically, how many would you go to in a year?
Well,
it's probably a bit of a difficult question.
Doing this since 2010 with TQ, so I can go to maybe 7 or 8 countries in a year, or go to 4 or 5 and spend a long time in those countries. So every year is different.
Right.
This year is going to be different for sure.
Oh gosh, yeah, really is.
Yeah.
Well, have you travelled already earlier on this year to any countries? You did, didn't you? I'm sure you did.
Yeah, I went stateside to Wisconsin, Green Bay, which was
yes.
We had a great experience there. Installed in 5 labs, fluids, controls, materials, and engines, which was a whole range of our product range. It was really a dynamic stay. It was a 2-week trip, very intense, a lot of unpacking, 18 wooden crates to undo when we got there. So that's a thank goodness for cordless drills, you know. But very satisfied customer, makes my job very satisfying when we come away with such a good result. It was very good. Yeah.
They did launch a new facility, didn't they? I saw all their press coverage about it.
And I believe LabMove West are working with you for testimonials, case studies, and so on. So yeah, all in all, a great story from start to finish. Yeah.
Brilliant. Good. Right. Okay. Where are we with time? Well, we're only on the scheduled time because we did start early. So I feel like we still need to do some filler stuff. Just for those, eke out the filler.
Yeah.
You know what I've got the Guinness World Record book here.
Oh, is it the latest one?
It is the latest one, yes. Your fact of the day was the first person to fly horizontally And the 24th of June 2014 was Swiss aviator Yves Rossi, who flew 4 minutes at a speed of 180 kilometers, some 1,600 meters above Yverdon airfield near Lake Neuchâtel in Switzerland. Excuse my pronunciation. There we have a lovely picture. It's not going to show it because I've got this stupid blurring background.
No.
But he
I mean,
has
it's
got
hard
this.
to. It's difficult to imagine anyone flying vertically, because then you'd just be called falling, wouldn't you? You know, gravity. You'd be falling at 10 meters per second, whatever.
He had 2 kerosene-powered jet engines fitted to 10-foot foldable carbon wings.
Madness.
It is. It is.
Wow.
There we go.
Yeah.
Well, that was your Guinness World Record book fact for the day. Right.
Okay.
Let's welcome to everybody who's just joined us online. We are live on YouTube. If you're watching this on demand, then please do put your comments in the comment box below and we'll try and get back to you in due course. If you are watching it on live, put your comments in the comment box below and we'll get back to you in the next half an hour. Right, so Dave, while people pluck up the courage to put their comments and questions in the comment box, I've got some questions for you. One of them is, which question am I going to give you? Which one?
Make it easy. Make it
Make
easy.
it easy, right.
No.
Well, this is a
Fine.
nice, easy one. Heat exchangers, understanding how heat exchangers work. Why is it important to understand about different heat exchangers, for example, and what courses might you do that?
All our heat exchangers on like on the TD360, so the flat plate, jacketed core and stirrer, concentric tube, etc. They're all scaled down models of what we see in the real life. Okay, you can walk into an oil refinery and see a concentric tube heat exchanger almost the size of the building. Okay, so it's absolutely critical to work out or appreciate and discover which is the most effective for that application in real life. Okay, so I know it's either the concentric tube or the other one is used mainly in oil refineries. Okay, so it gets the students a real hands-on appreciation of what one is best for a particular application. Okay.
And that other one would be, I've got the website now, so I'm going to cheat, is the shell and tube heat exchanger. Brilliant. So Dave, now these all mount on this benchtop unit.
Yeah.
How big a job is it to swap one over from the other? Do I have to do one lab session on one, come back the next week and do another cell lab session on another?
No, not at all. No, these are very, very quick swap overs. You have 4 screws that clamp the heat exchanger and its base to the platform, the TD360 main service module. Once you've undone those screws, assuming that they've turned off the hot and water supplies with the needle valves, they then unplug the quick release connectors. They are self-sealing, so you may get a few drops of water along the way, but they are self-sealing, so you just put them to one side. You grab your next heat exchanger, you screw it down to the base, reconnect the hot and cold water pipes, depending on whether they want to do concentric tube or parallel flow or concentric flow. Then you're good to go. You then switch on your water supplies, open the needle valves to get the right flow rates, make sure your temperature probes are connected to the right sockets on the back panel, and then you're good to go. It's very simple and very quick.
All right, great, brilliant. On to another question now. What are some of the most commonly asked questions that you get as customer care? I know you get asked about strain readings, for example. Maybe you could talk about those, and maybe any other commonly asked questions that you get in customer care that you feel like you could just add a bit of clarity to the people watching this today.
Yeah, well, you touched on one of the most commonly asked questions just then, Dion, and that's the strain readings don't match, or our results don't match what's in the manual. You know, and then it's kind of natural. to think there's a problem with the equipment when in fact there's not. But the key to all of our experiments, without exception, is the setup. So with the structures range, STR17, STR5, STR8, where they're all using strain gauges, we need to take out all that friction, all those looseness in the connections of the truss, for example. So we need to apply a preload. So we connect it all up. We then wind down the STR8A load cell. We then put the whole thing under a load, but then we zero it on purpose. That removes the sticking and the friction.
The word of the day.
You're good to go. That's a good word. And it does exist in our manuals. You'll see that in our STR8 manual for sure. Okay.
Now you just explained on Instagram. We did a live stream on Instagram a few minutes ago, and we talked about stiction. Can you explain for everybody watching on YouTube what stiction really is?
It's a combination of sticking and friction that you get, for example, on the pin jointed frameworks. At each junction, everything is loose. Okay, and if you were to take readings from that point when there's looseness, you get poor results. So we need to start off from a point where there is no looseness, where everything's nice and tight, all the friction has been removed, and any sticking has been taken up by that preload. So it's absolutely critical. That's the most important thing to note with the setup, is getting rid of that anomaly. Okay.
Well, I'm pleased you explained stiction, because Wikipedia's definition is really not as clear as you are. They say stiction is the static friction that needs to be overcome to enable relative motion of stationary objects in contact. You've made it so much, yeah, but you've made it so much simpler.
But no doubt Wikipedia, they copied TQ for sure. No doubt.
Absolutely, yeah. Go to Digital Day for the answers on stiction.
Stiction. Yeah.
Great, good. Now our tensile testing now.
Tensile.
Yeah.
Stretching and breaking.
Yep.
Yeah.
Now we've got a couple of different tensile testers. I'd like to talk specifically about a universal one, the big one that really is very engaging. It's one of our really popular products. Dave, now this isn't just about breaking stuff, is it? No. However much I like to have a go breaking stuff.
I love breaking things on purpose, mind.
Yes, yes.
I must add, I don't break things when they're not meant to be broken.
So tell us, it's not. What else can we do with that particular piece of apparatus? I'm going to pull it up so everybody knows what I'm talking about. Once
we've carried out the tensile test, we can then move on to hardness testing. So we include not include, but as an accessory, you can purchase the Brunel test. So it's a very basic hardness test. Then we can look at leaf springs. We can do a coil spring experiment to look at the spring rate or the stiffness of the spring. We can do, like I said, coil spring, leaf spring, beam, and this cupping test that we just added to our product range. So there's about 5 or 6 different experiments that can be done on the SM1000. Going back to the tensile test, not only can it just do a basic load over extension in the range, but we can actually do a Young's modulus test. So we have an extensometer that we can attach to the specimen. This measures very small movement of creep. So with having that, we can actually do a stress over strain test. Okay, and if we calculate the gradient of our graph, that will tell us the Young's modulus. We can also calculate the Young's modulus, but just by determining the gradient of our stress over strain graph will tell us the Young's modulus. These are all keywords in material testing.
Great. So if anybody has questions about Young's modulus, do put them in the comment below, and we'll get Dave to come right back to you on that.
Sure. Yeah.
Now, beams in this piece of apparatus. This is, yeah. How do we deal with beams in this particular? Not beans, not Jack in the Beanstalk, magic
Well,
beans, but
yeah, with
beams.
the beam testing option, you need the help of possibly 2 more people, because the beam support needs to be lifted. It needs to be like eased through the working section, so it's in the center, and then you have a big heavy bolt that secures the beam support. Then we can fit the beam to its normal position. We then use the digital vernier overall extension gauge. This sticks, because it's magnetic, it sticks to the beam. So then we've got beam deflection and we've got load applied. It's a non-destructive test, so we don't bend the beam. It's just done within the elastic limit of the beam. So it's in the elastic region, not plastic. Okay. Do not go past the elastic limit, or customer care will be receiving a phone call or an email, I would think.
How do you know when you're getting to the edge of that limit, though? I might just carry on pumping the lever and merrily waiting for it to do something.
You know, from a number of reasons. First of all, you can actually sense it in the hand pump, which
Okay.
that's the MF40 there. That's not the SM1000. SM30. Yeah, you get feedback through your arm, Dion. You know when the effort that you're applying to the hand pump, when you sense it's easing off, when you continue to see an increase in extension, but the load itself seems to plateau, it seems to tail off, that's when you know you're going from elastic to plastic. It's called the limit of proportionality, or yield point. So there's 3 or 4 alarms, if you like, that should flag up when you know you're getting to that point. Okay,
right. So when it starts easing off, just stop before you cause damage.
Yeah. Yes, you will. Yeah.
Okay. I just want to say hi to the new people that have joined us on YouTube live right now. Please do comment in the box below if you have questions for Dave. We'll put them to Dave and he will answer with all of his great wisdom.
Yeah.
Right. While we leave people to type out their questions, I've got one that's just come in, and it's about looking at air bubbles.
Well, you can go to any toy shop and buy some bubbles if you like.
I'm forever blowing bubbles.
Yeah.
How do you remove the air bubbles out of, say, a H10? Let's have a look at a H10 so everybody knows what we're talking about with a H10.
It's a flow measurement apparatus where we use different methods for calculating the coefficient of discharge or flow rate. So we have a venturi, we have an orifice and a rotometer, and a row of manometers to look at the heads across each of those pressure tappings. Okay, but once we first connect it to the hydraulic bench, invariably, just by its very nature of the design, we get air. So once the hydraulic bench is switched on and we've opened up the valve on the H10, which you can just see there in the background, it's on the left hand side and it's got a red hand wheel. Water will be introduced into the experiment along with air. Air will be then naturally pushed up the manometer tubes, but we're able to actually vent that air by way of a bicycle Schrader valve. So we just use your fingernail and we press that Schrader valve. Air and water will rise up through those manometer tubes and vent. We then close off that valve. Then with the hand pump, with the bicycle pump supplied, we connect that to the Schrader valve, and about 4 or 5 sharp pumps will lower that water level to a workable level, say 300 millimeters, and then you're good to go. You are good to go then. A little bit of air didn't hurt anybody, but huge pockets of air, you will have a problem. And you can see that because of the benefits of having the clear acrylic working sections of the Venturi. You can actually see where the air pockets congregate, so you can take action accordingly.
All right, that's good. Okay.
Can you actually see me, Dion? Because I'm not sure My camera is showing.
Yeah. Oh, yeah, I
Okay,
can see you. Yeah,
but
it's all good.
I can't see myself, so I'm going to have to take your word for it that I look as good as ever. Okay.
You look amazing, Dave. You've got your flags behind you, your curtains there.
I'm not sure why I can't see myself, but
You've
you know.
changed your top this morning.
Yes,
You've
yes.
gone
Well,
from polo shirt to t-shirt. Did you spill your dinner down the front?
no, no, no. It's got so warm in Nottingham. I've had to, take measures to cool down.
Well, it definitely hasn't up here in the hills. I've got the fire going, keeping us warm. I've
Right.
not had to go as far as getting the hot water bottle and blanket out today.
You'll have to get on your horse and go and get some firewood.
Well, you know what? We have been up on the bonfire today, helping out with the burning of fire and bringing more logs down from the fields.
Don't go in the dark. Do not go out in the dark. There'll be demons in them woods. I'm telling you, there'll be demons.
Hey, I'm from the country. I can cope.
So am I. I'm from the New Forest. I was born and bred in the New Forest. I mean,
Industrious people we are then.
Yeah.
I've got a question now. Can you talk about, with wind tunnel, say the AF 1300 subsonic wind tunnel?
Yeah.
How would you do a lift and drag experiment just for students who are still trying to write the reports?
Yeah.
Can you tell step by step us through that process? Before we do that, I just want to say hi to Emilio. Emilio has managed to join us. Emilio, you sent me some questions earlier. I'm going to try and pull them up quickly from my email so that I can ask Dave once he's done this bit about describing a lift and drag experiment.
Yeah, well, to do a lift and drag experiment, you need models. Okay, you need to have either aerofoils or three-dimensional models in your wind tunnel. Let's assume you have NACA 0012 symmetrical aerofoil. With that mounted in the wind tunnel, you need to measure somehow. So we need a balance, either a two-component balance to measure lift and drag, or a three-component balance to measure lift, drag, and pitching moment. Okay. So to measure those values, we are able to turn the model in degrees, in 5-degree steps, 10-degree steps, up to the stalling, and then you'll use the three-component or the two-component balance to measure the force being applied in newtons. So we know the force applied, we know the wind speed, either calculated by yourselves using the manometers or using VDAS that's already calculated the wind speed. So once we've got the raw data in newtons, we can then apply that to quite a straightforward formula that's in the manual, and that will allow us to calculate the coefficients of lift and drag, and also look at the pitching moment if you've got the three-component balance. So it's a very straightforward test. It's quite easy. So you just choose whether to do it analog or digital, really.
Okay, fair enough. Well, I've just checked back at Emilio's email. You've got no specific questions on there, Emilio, but if you do want to address any of your specific topics, then do put them in the comment box below.
Yeah, or email Dion or customer care inbox at Tech Equipment, and we'll get back to you very soon indeed.
Now, this is going to be available on demand, so many people will be watching this on demand afterwards. We'll put some links, email addresses in the comment box below. A reminder to everybody that we will be doing these live streams every Wednesday. You can either join us on Instagram or YouTube and have your questions at the ready.
For sure. Yeah.
Good.
Okay.
Now, I've got an interesting question about virtual experiments, actually, in the structure software. Now, I know we can use data acquisition with the structure in the structure software, but can it work standalone? I believe it can, but can you clarify how that all works?
Yeah, well, for that to work, the customer will need to have ordered the STR 2000, okay, and that will that's our automatic, that's our data acquisition just for the structures, okay.
So that's different to VDAS, isn't it? We've got VDAS and we've got Structures has its own separate data acquisition software.
It does. It comes with a concise manual for all the experiments. Also comes with a key to unlock the software, and then you can do your experiments. If you want to do a virtual experiment, the benefits of the STR2000 is you may just have one hardware, you may have a bending moment or shear force, pin geometry frameworks, but having the STR2000 unlocks all 19 structures experiments to be able to do a virtual experiment. Okay, so within the software, instead of clicking connect to the hardware, you go across to another cursor, another icon. It's a little wizard, literally it's a wizard. You click on the wizard, that puts you into virtual mode. Okay,
right.
You can then select one of 19 experiments and you can carry out the experiment virtually. You don't need the hardware. The beauty of it is you are quickly and easily able to change the material type, for example, the diameter, and you can even change the Young's modulus because it's virtual. You can actually test a beam to destruction because you're not actually testing an actual piece of equipment. It's all virtual. So it's a very, very useful piece of kit because you could project that to a big screen in the classroom. You can do classroom demonstrations where they can all observe and all take readings of the parameters that are being measured. So, and I use it a lot out in the field because it backs up and corroborates the actual piece of hardware that I've just installed. So it confirms that it does exactly what it says on the tin. Okay, so it's very useful.
Brilliant. Good. That was really helpful. Thank you, Dave. That clarifies that one. Now, I think that's probably about it for today.
Okay then.
We'll have a few more links of other videos coming up. Thank you very much, Dave, for your time. Enjoy the rest of your evening. All the unlimitless opportunities that you have from the rooms of your house.
Yeah. I don't know where I'm going to have tea tonight, whether it's in the kitchen, in the lounge. It's mind-boggling.
Oh my gosh, the options. I think I might even have to venture out to the supermarket and join the queue in the car park that's 2 meters apart, to be honest.
2 meters apart, yeah.
Yeah, I think it has to be done. We're running short on some of the essentials before we have to start getting creative with our combinations. So that's it from us. Thank you so much to everybody who's joined us today, who's watching this on demand. Don't forget to join us again on Wednesdays live on YouTube and Instagram. This is me, Dion Knowles, and Dave Giddings. Goodbye.
Yeah,
thank you.
Cheerio. Bye for now.
Right, I do know that it does stop when we stop live stream, and goodbye.